Good morning, everyone. How was everyone's break?
Pretty good.
I'm just happy to be back. My wife put me to work in the backyard again, so there we go. Got scratches, bruises, and everything all over the place. But anyways, so just to remind you what we were talking about before we went on break. So we started capacitors again. So again, we said that we have a capacitor, which again is two conductors spatially separated by some distance d. That if we measure the charge on the capacitor versus the amount of potential which is supplied by the battery, we find is that there's a linear slope between the two, which is what we call the capacitance capacitor, that's C here. So we found the charge then is equal to the capacitance times the potential, which means capacitance then is equal to the charge divided by the potential. In a special case that it's parallel plate capacitor, then we can analytically solve this to find that capacitance is epsilon naught times the cross-sectional area, where again each plate has exactly the same cross-sectional area, divided by the distance d, where again the distance d is the separation between the two plates. We looked at parallel and series, where again, remember in parallel means the potential is the same, and we look at them in series, that means the charge is the same. So to add capacitors in parallel means we simply add them together, so it increases the size of the capacitance when we add them in parallel. So in this case, the equivalent capacitance of those capacitors in parallel is simply equal to the sum over all the different capacitors. And when I add them in series, the overall effect again is to decrease the size of the capacitance. But in this case, we add them inversely. So 1 over CDQ is equal to the sum over the inverses of all these capacitors. So this is parallel and series. So again, the effect of each one of these is again, this one increases the capacitance, and this one decreases the capacitance. So the last thing we looked at was we said, okay, so the whole entire point of capacitor is to store energy, and it stores energy by the battery doing work onto the capacitor to store the charges onto the capacitor. So in this case, the energy which is stored is then equal to the work done by the battery, which is equal to any one of these three things, whichever one that you like, or whichever one you know the most information for. So it's 1/2 times the charge squared divided by the capacitance, or 1/2 the capacitance times potential squared, or 1/2 the charge times the potential. Again, each one of these just says a different thing. So they all say the same thing, but again, this one says that the energy is stored within the charge. This one says that the energy is stored within inside of the potential. And then this one says that the energy is stored in both charge and potential. Now, it turns out there's an alternative way we can look at where the energy is stored, which is something we haven't talked about yet, which is what's known as the energy density. So what is the energy density? So again, let's go back to the energy. So we know the energy is equal to, I'm going to use the second one here, 1/2 the capacitance times the potential squared. Now, if we pretend for a moment that we have simply a parallel plate capacitor, so here's my parallel plate capacitor, which again has the potential difference of B across the plate, so this is my B, then we can rewrite the capacitance in terms of the parallel plate capacitor. So again, from the previous slide, that's just epsilon naught times area divided by the distance. And we know that the electric field, or at least the potential here, is related to the electric field, where my electric field is pointing down in this direction. Where from last chapter, we know that the electric field is simply equal to the potential divided by the distance, which means by potential in this case, it's going to be electric field times the distance. And again, we know this one is true here because the electric field is constant everywhere in between the plates. This was not constant. This would not be true. I'd actually have to take a derivative in this case. But let's plug that in then. So from here, we can say the potential is also equal to the electric field times the distance squared. Good. So let's multiply all this out. So it's going to be the same thing then as what the energy is going to be 1/2 epsilon naught times the area divided by the distance times the electric field squared times the distance squared. But this distance here cancels out one of these. So it's going to be the same thing then as 1/2 epsilon naught times the electric field squared times the area times the distance. Well, what's area times distance? What do we call it? What's area times distance?
That's the volume.
That's the volume, right? Kristen, did you have a question?
No, I'm good.
You're good now, okay. So it's going to be the same thing as 1/2 epsilon naught times the electric field squared times the volume. So from here, we can define a new quantity. This new quantity is what's known as the energy density. So we can say, well, the energy density, which is little u, is equal to capital U per unit volume, which means this is simply equal to 1/2 epsilon naught times the electric field squared. So energy density then has units of joules per meter cubed. So this is how much energy there is per unit meter. Well, what this one basically says is that, well, the energy is actually stored within inside of the electric field itself. That's what this one is actually telling me. So this one says that the energy is stored within the field itself, not the charge or the potential. So this is actually a much better interpretation. So what does the energy density mean? So again, this means that if this was my parallel plate capacitor, so here's my parallel plate capacitor, I'll be up here. Guys doing something like this. Here's my electric field again pointing downward. What this thing means is if I go in here and I chop out some small volume here, so this is the volume, what this thing is then saying is that the amount of energy inside of this volume is then simply equal to the energy density multiplied by that volume. So it is basically telling me is how much energy do I have in any random amount of volume that I take out of the electric field itself. So inside of here, this is the energy density. So the amount of energy which is actually stored inside of the electric field between the plates. And then if I want to know the total amount of energy I stored, all I have to do then is multiply the volume that's stored within inside of the plates itself. Okay, so this is what we call the energy density. So again, it's just the same information. It just means how much energy is stored per unit volume, which means the total amount of energy is simply the energy density times the volume. But it's just another interpretation on where that energy is being stored. So in this case, the energy is being stored within inside of the electric field itself, not within inside of the charge or the potential. But again, it's just the same information as before. It's okay? So this is what we call energy density. We'll talk more about this later as we need be. So good. So the last topic we're going to talk about in this chapter is what's known as a dielectric. So what's a dielectric? So a dielectric is a material that we can add to a capacitor to increase the capacitance of the capacitor. So a dielectric is a insulating material. That's on page good. Added to the dielectric, or sorry, added to the capacitor to increase the capacitance of that capacitor. So this is what we call a dielectric. So a dielectric is simply an insulating material because it has to be an insulator. Or we're simply going to add that inside then of a capacitor to overall increase the size of the capacitance. So if this is my capacitor, here's my parallel plate capacitor. In this thing, all we're going to do is we're going to put in a dielectric material. So here's my insulator. I'm going to put inside of my dielectric, where the overall effect of this thing then is to increase the capacitance of the capacitor. So this is my dielectric. So the point then of the dielectric is then to increase the size of the capacitance of the capacitor. So it turns out that the reason that this works is because, as we know, we talked about the difference between insulators and conductors, is that when these guys are charged, this thing doesn't have charges which are allowed to freely move, but it does allow for polarization. And so I get small charge separation, which allows for small polarization on the inside. So for example, let's say this is my positively plate charge. This is my negatively plate charged. So again, what's going to happen is I'm going to get a separation on the inside. So what's going to happen then is that negative charges are going to be attracted to the positive charges. The positive charges then will be attracted to the negative charges. So I'm going to get these small types of dipole moments which are going to be created inside of my dielectric. So inside of here, all I'm doing is I'm creating little dipoles. Each one of these guys is going to create a dipole. Now, the overall electric field from, say, this plate points from the positive charge to the negative charge. So this is the electric field from the capacitor itself. But on the inside, I'm then going to get this polarization. So this separation, meaning each one of these dipoles is going to create an electric field, which then points in the opposite direction. So this is my electric field of the dipole. Which basically means that the net total electric field inside of the capacitor now has decreased in size because I have to vector sum these two guys together, but this one points in opposite direction to this one, and then decreases the overall size of the electric field. But if this thing is connected to a battery, the battery, or at least the potential across the capacitor, is dictated by that of the battery, which means I can now put more charge onto the capacitor plates to increase the overall size of the electric field, meaning increase this electric field, so that the total electric field on the inside matches what it should be based off of the size of the battery. Okay. So ultimately what that does is it allows for more charges to be stored outside of the plate, which allows me to have more energy stored within inside of the capacitor itself. So overall, the effect then is to increase the overall capacitance of the capacitor. So how does it actually increase? Well, it turns out that the capacitance of the capacitor then decreases by an amount of what's known as the dielectric constant. So in this case, the new capacitance of my capacitor increases by kappa, which is another type of K. So I'm going to try to make it look like a kappa, but it's a K, it's a Greek K, right? Times the original capacitance of the capacitor. So C0 here is the original capacitance. And then kappa here is what's known as the dielectric constant. So what then is the dielectric constant? Well, the dielectric constant is, it's in reference to what's known as the breakdown potential. So the dielectric constants defined in terms of the breakdown potential of the insulator. What does that mean? So that means, like, especially if it was in the middle of the winter, I'm scrubbing my feet across the floor because I'm too lazy to take my damn feet and walk across the floor. It's 9 o'clock in the morning and I can't wake up. And then I go to grab the door handle. What happens to me in the middle of the winter? I get shocked, right? Now, if I get my hand close enough between the door handle and myself, I'm creating a parallel plate capacitor. This is what I'm doing. What happens when I get shocked? What do I see? I see a spark, right? I'm going to see basically electrons jumping from the one to the other one, which then causes me to spark, right? So in this case, the electrons are actually jumping off of me onto the door handle, which then causes a spark. This is what we call a breakdown. So what happens in a breakdown is that the potential difference between my hand and the door handle becomes so great that the air will actually ionize, hence creating a spark, because I'm discharging myself by touching that door handle. Okay? So this is what we call the breakdown potential. It turns out that dielectrics have a much higher breakdown potential than that of air. So it takes more potential difference between the door handle and my hand if I had something like plastic between my hand. In that case, the breakdown potential of plastic is much higher than that of the breakdown potential of air. So one good thing you can actually do in the middle of the winter to actually discharge yourself is carry around a screwdriver. So if you carry around a screwdriver, before you open the door, take the screwdriver, touch the door handle with the screwdriver, and then you can open the door and you'll never get shocked. Okay? The reason for that is you're going to discharge yourself through the handle of the screwdriver, but since the breakdown potential of the screwdriver's handle, i.e. the plastic, the insulator, is much higher than that of air, you're never going to get shocked. Okay? So this is what actually causes you to shock. So the dielectric constant then is the ratio between the breakdown potential of the dielectric, i.e. the insulator, and that of the breakdown potential of air. This is the way we define the dielectric constant. So kappa then is then equal to the breakdown potential of the insulator divided by then the breakdown potential of air. So this is what we call the dielectric constant. Now, what happens then is that this thing is only equal to 1 when I have air. Because then the breakdown potential there divided by the breakdown potential there is simply equal to 1. Anything else has a higher breakdown potential than that of air, at least any dielectric, i.e. any insulator, which means this number will always be greater than, only equal to 1 when it's air-filled. So if I have an air-filled capacitor, all that means is I don't have a dielectric inside of there, so this thing is going to be equal to 1. If I have anything else in there, this number then has to be bigger than 1. This is what's called a dielectric. So the overall effect then of putting a dielectric then into a capacitor is to ultimately increase the capacitance by the size of that dielectric constant. This is the point of putting it in there. The physical reason for that, again, is that it decreases the size of the electric field due to the polarization of the material on the inside, allowing me then to put more charge onto it, which means that I'm increasing the capacitance based off the size of the potential. Because I'm not changing the potential that's fixed by the battery itself, but what I am doing is I'm increasing the size of the capacitance by decreasing the electric field, allowing me to store more charge on it. So this is the physical application of a capacitance, at least of a dielectric within inside of the capacitor. Now, the overall effect on the amount of energy I can store and et cetera is going to depend on how I insert that dielectric inside of the capacitor. Whether I'm inserting it when it's plugged into a battery or if I'm inserting it when it's not plugged into a battery. So let's look at what happens in those two different cases. So let's look at the effect of it. So we're going to have two distinct different ways. We're going to have it when it is connected to a battery. And then we're going to look at it when it is disconnected. So what's the difference? So in the first case, I'm going to take my parallel plate capacitor. Here's my parallel plate capacitor. I'm going to allow that then to be attached to the battery, where the battery is supplying an amount of potential of V, and we want to see what happens. Okay. So initially what happens is this thing is going to have a charge on it of Q and minus Q, which means there's going to be an electric field on the inside pointing down in this direction. Okay, so this will be my electric field. Now, what I want to do then is take my dielectric here, and I want to insert it inside of my parallel plate capacitor. Disconnect it. I'll do that on another slide. So I want to know what happens. Okay. So what happens then is, so let's bring this over here. So here's going to be now my battery connected then to my parallel plate capacitor. But now this guy now has a dielectric material on the inside. So let's again talk about what happens. So again, first things first is potential across the capacitor must still be the same as the potential across the battery by conservation of energy. So again, saying if I start at a point here, I have to increase the energy by an amount of V, go through here, decrease by an amount of V, come back to the same point to have my loop rule say I have zero change of potential. So in this case, what has to be true then is that my final potential must be equal to the initial potential. This has to be true. Now, what happens then? As we said, what happens is I now get polarization inside of here, which decreases the size of the electric field, which means that I can now put more charge onto the parallel plate capacitors to ensure that the potential stays the same. Which means then that the new charge, which is on this plate, is greater than the original charge. And it's greater than the original charge by an amount of the dielectric constant. And so what happens in this case then is that my charge overall increases by an amount of the dielectric constant. What else happens? Well, if my charge is increasing, that means my electric field also is increasing, which means my electric field is also going to increase by an amount of the dielectric constant. Finally, the energy that's being stored then, well, if I have increased the amount of charge, but I have left the potential the same, what happens in this case then is if we go all the way back to this slide, this guy has increased, this guy has stayed the same, or this guy has increased and this guy has stayed the same, which means the energy also increases by an amount of the dielectric constant. So in this case, the energy which is being stored inside of the plates also increases by an amount of the dielectric constant. The amount of energy which is initially stored between the plates here is now increased due to the fact that I have inserted this dielectric. Is it okay? And now what happens when it's disconnected? So in this case, what we're going to do is again connect our parallel plate capacitor to a battery. Here's going to be my battery. So this is at B, and what I'm going to do is I'm going to charge this thing to a maximum amount of charge Q, so that this thing has a charge of negative Q. Then I'm going to disconnect it from the battery. So I'm going to pull this thing out, so that now I just have my parallel plate capacitor, which is then at a charge of Q and minus Q. And then from here, what I want to do is now stick my dielectric material on the inside. Here's my dielectric. Again, I want to bring this inside of the plates. And I'll show you a simulation of all the stuff too. Cool. So now what? So now from here, what's going to happen is we're now have my parallel plate capacitor, which is now going to have a dielectric on the inside. So here's my dielectric. And let's talk about what happens. So first things first. That charge first, or not charge?
I'll just go ahead.
Is that a question? Okay. So first things first. Let's think about the charge. How did the charge on the parallel plate capacitor change going from here to here? Did it increase, decrease, or stay the same? And why? What do you think?
Had to stay the same.
Good. Exactly. Fantastic. So in this case, what happens then is that my new charge on my parallel plate capacitors is actually equal to the original charge. As Tim was saying, there's basically no input and there's no output, right? Which means that when I shove this parallel plate capacitor or this dielectric inside the parallel plate capacitor, there's no place for the charge to go. Which means I have no battery here to put more charge on, but I also don't have a closed loop here, which means there's no cord connected to this guy for this guy, which allows then for the charge to go someplace else. That charge is forced to be on that dielectric or on that capacitor, and it can't go anywhere, has no means of going anyplace else. Which means when I stick this guy inside of here, it has to then stay exactly the same. Now, but when I put this inside of here, I now get what? A polarization on the inside, which means that my electric field is going to decrease. What happens then to the potential difference between the plates going from here to here? What happens now? So here again, I have a potential difference V. What happens to the potential difference here? Did this guy increase, decrease, or stay the same? Is actually decreased. The reason the potential difference has decreased now, again, is I'm getting polarization on the inside, which means I'm creating an electric field on the inside opposite to the direction of the electric field on the interior, which means the total electric field has decreased. If the total electric field has decreased, that means the potential has decreased as well. Which means also the electric field magnitude has decreased by an amount of the dielectric constant. Finally, what happens to the energy? Well, in this case, the energy is what? So let's go back to our equation here. There we go. So in this case, again, if the charge has stayed the same, but the potential has dropped by an amount of the dielectric constant, that means the energy has also dropped by an amount of the dielectric constant. In this case, my energy stored has dropped from the original by an amount of the dielectric constant. Okay?
So if we had this, right, and so if the potential is different, and say in the lab, we we connected our light bulb after we had stuck the dielectric in, would we not, why would we not get the same result of the light bulb lighting up for X amount of time?
So why would we?
Like, well, the energy has to go somewhere, right?
Correct. So the energy in this case is going to go to putting in or taking out the dielectric. So remember, when I put in the dielectric, I have to do work onto the system to get it to move it in. As opposed to when I pull it out, I have to do work on the system to pull it out. So in this case, it depends on how I'm inserting it to then change the amount of energy. So let's think about it this way. So in this case, since I am now decreasing the potential, which means I am decreasing the energy, how is that going to affect the capacitance? So meaning that when I go to put the dielectric inside of here, since it's decreasing the overall size of the energy, is that an energetically favorable thing to do or not to do? So remember, we always want to be in the lowest energy state as possible. Make sense?
Okay.
So when I go to insert the dielectric, what happens in this case? What happens in this case then is that the capacitor itself will actually suck in the battery, or not the battery, but the capacitor itself will actually do the work to pull it in. So I'm losing energy due to the fact that I have to pull in that dielectric. That makes sense? As opposed to, go back to here, if I was trying to insert this guy then into this scenario when it's connected to the battery, does it want to be added when the battery is connected to it? Well, no, because I'm now going to a higher energy state, which means I have to do work onto the system to then push that into there, which means I'm overall increasing the amount of energy in the system by me forcing that dielectric into there. It's gonna make sense? So, good. So your question, where did the energy go? Well, in this case, the energy went, if it was disconnected from the battery and then I added to it, the energy went into this thing sucking in the dielectric inside of itself. So the energy went into partially pulling that thing in. So this is where the energy basically went to. Now, your overall question then is, well, what would happen to the charging time? Well, again, the charging time, discharging time wouldn't change because the amount of charge is the same. So since I'm fixing the amount of charge, and what we have to do is rearrange all the charge, so the charging time versus discharging time actually won't change. But the energy which is contained inside of that dielectric, inside of the capacitor, would change. So I wouldn't have as much energy, but the amount of time it would take to redistribute the charges would actually stay the same. That make sense?
Yes.
So you're asking fantastic questions. So the question, or the difference between the two scenarios, is in this case, it's more energetically favorable for the dielectric to be inside of the parallel plate capacitor, which means parallel plate capacitor is actually going to suck it directly in. So once I start putting it in, it's more energetically favorable, so it's going to pull it inside of itself.
By sucking it in, do you mean like the adjustment of the dipole within the insulator?
Right, so both the adjustment of the dipoles as well as the charge on the plates themselves. Because the plates, so the charges on the plates will actually move around themselves because it's a conductor, so they're allowed to freely move. But in this case, since this thing is forced to be at a particular potential by the battery, in this case, it doesn't want the dielectric because it's more higher in energy, so it wants to force that thing out. So I have to do work onto the system to then push it inside of it. Does all make sense?
Yes.
Go. So let's kind of see all this work in, that this will also bring in this little simulation here. So basically all I have here is a battery connected then to parallel plate capacitors. I'm going to show different things on here. So let's show the capacitance. Let's show the plate charge. Let's show the energy stored. And let's look at a voltmeter. Also the electric field. So good. So let's go ahead and turn on the battery. Good. So here's my battery. So initially what's happening is, so in this case, I have, there we go. So initially, this is just my parallel plate capacitor. As we said, the parallel plate capacitor depends on the area and the distance. So one thing we said is if we decrease the amount of distance between the two, then I'm trying to just move the geometry, but it's not doing that. Oh, well. already know that anyways. Let's talk about a dielectric. So let's just show this case because this is more relevant anyway. Turn this on. There we go. So good. So in this case, here's my amount of charge on here. So again, let's show the same thing. So let's show the dielectric, plate charge, energy stored, and electric field lines, and a voltmeter. Okay, I'm going to leave this separated because I don't want to change anything too much. So initially, this thing has 1.5 volts across it because that's what my battery is doing. So in this case, I have my dielectric on the inside, on the outside, and let's look at what happens as I move this thing in. So again, this is the first game we looked at. So I'm going to push this guy inside. Go. So again, as I'm moving it in, you can see all the charges kind of realign themselves on the plates. You can then see all the dipoles creating on the inside of the dielectric. So as I insert this guy inside of it, again, what happens is the capacitance increases, the plate charge stayed the same, or sorry, increases, and then the energy also increases as well. But the potential stays exactly the same between the two. Okay on this? So if I look at my electric field lines, again, I have overall electric field lines going this direction, but I also have small electric fields on the inside, which then changes the overall size of the electric field. Now, let's do the same thing, but I'm going to disconnect the battery. So here's my disconnected battery. And again, let's look at what happens in this case. So again, as I start to move this guy in, go. So now, again, you can see the charges realign themselves. You can see the dipoles creating on the inside. And what's happening now, again, is the capacitance is still increasing. That is still true. But the charge stays exactly the same. But again, the stored energy is going down because, again, the size of the electric field has decreased because the size of the voltage has also decreased. So again, the overall effect onto the energy as well as the electric field as well as the charge all depends on how it's connected or how it's inserted inside of the capacitor. So is it inserted when it's disconnected from the battery or when it is actually connected to the battery? What's up, Chris?
So whenever it's disconnected, does it have an initial voltage?
We have to usually put an initial voltage on it. You don't have to. I mean, you can put it in there when it has no charge on it. And then in that case, it doesn't change anything about the charge or the potential or anything. There's none of those stuff on there to begin with. Okay. So good. So let's use this and let's look at an example. So this says we have a pair of plates capacitor built with a dielectric with a dielectric constant of 3.4. It's connected to a battery which has 100 volts worth of EMF. So after the capacitor is fully charged, the battery is disconnected. And it tells us that the plates have an area of 4 meters squared and separation distance of 4 millimeters. Then it wants us to find the capacitance to charge the capacitor, pardon me, charge on the capacitor, the electric field strength, and the electric field or the energy stored initially. Okay. Ooh, I can say all that. Good. So, why did you do that? Fair enough. So good. So what I have is, again, here's my system connected initially to the battery. Here this guy is, and initially it starts off with my dielectric. Here's my dielectric on the inside. So the dielectric constant is equal to 3.4. So the battery then has a potential of 100 volts. Wood. And we also know the cross-sectional area in this case is equal to 4 meters squared. And then we know the separation distance between the two, D, then is equal to 4 millimeters. So this guy now is going to be disconnected. So we're going to put it down here. So now this guy is going to be sitting here by itself. Great. There we go. And now we want to know our certain things. So we want to know what is the charge. So let's call this the initial charge. We want to know the potential. So let's call that the initial potential. We want to know the energy which is stored. So let's call that the initial energy. Am I missing anything? The electric field strength. Okay. We also want to know what is the initial electric field strength. Fine. So let's talk about the capacitance. So first of all, we know the capacitance is simply equal to the dielectric constant times the initial capacitance. which is then going to be equal to the dielectric constant times epsilon naught times the area divided by the distance. So this is going to be my capacitance of my system. So in this case, it's going to be equal then to kappa, which is 3.4, times epsilon naught, which is 8.85, times 10 to the minus 12, times the area, which was 4, all divided by the distance, which was 0.004. I'll look at my numbers. What I find in this case then is that the capacitance is then nanofarads. So 30 nanofarads is the amount of capacitance this thing starts off with initially.
What's on the end of? like,
That's a
where you put the
4.
number?
I didn't know how much room I had there for us. A little better. Let's see. So what am I looking for? Capacitance, charge on a capacitor. Okay. So there's that. Let's talk about the electric field. So in this case, we know that what the electric field initially is then equal to the initial potential divided by the distance between the two. Okay, so this is going to be equal to 100 volts divided by 0.004, which is the same thing as 25,000 newtons per coulomb or volts per meter. So this is my initial amount of electric field. My initial amount of charge then is then equal to the capacitance of the variable plate capacitor times the initial potential. So in this case, it's going to be equal to, what was it, 30 times 10 to the minus 9 times 100. Then going to be what, 30 times 10 to the minus 7 coulombs. So that's the same thing as 3 microcoulombs. Okay. The initial amount of energy then is then going to be equal to, so it's going to be 1/2 the capacitance times the potential squared. So let's use that one. So in this case, this is the initial potential. So it's going to be equal to 1/2 the capacitance, which was 30 in nanofarads, times 100 squared. It's going to be 1/2 of 30 times 10 to the minus 9 times 1 times 10 to the 4th, which is the same thing as what, 15. 15 times 10 to the minus 5. It's going to be 150 microjoules. Okay. So now what? Let's go back to our problem. So then it says the dielectric is now going to be carefully removed so that the distance d and the charge q stays the same. We then want to find out what are the values of the capacitance, the field strength of the electric field, the voltage between the plates, and the energy stored in the capacitor. So let's do that. So now what we're going to do is, here is now my capacitor. I'm going to pull out the dielectric material. And now what I want to know is, what is the new charge? It's called like Q prime. What is the new potential between the plates? It's called that V prime. And what is the new electric field between the plates? So let's call that E prime. And then finally, what is the new energy U prime stored between the plates? So what are all these different things? So what's the new charge?
So that was the same, right?
It's the same, that's right. So in this case, we know that my new charge is simply equal to the old charge, which was our initial charge. And we said that was equal to what? 3 microcoulombs. So it's going to be 3 microcoulombs. That's going to be my new charge. What's the new potential? Well, what we said was that when I put in the dielectric, what happens to the potential? When we put in the dielectric, what happens?
Decreases.
It decreased my amount of the dielectric constant, which means when I pull it out, what should happen to the potential? It's going to increase my amount of the dielectric constant. Okay. So in this case, my new potential then is equal to the original potential increased by the size of the dielectric constant. So this is going to be equal to 340 volts. So 3.4 times 100. Now what else do we want? We want the electric field strength. So we know the electric field strength then is equal to the original electric field strength. Also by an amount increased by an amount of the dielectric constants. So it's going to be equal to 3.4 times 25,000 volts, which works out to be 5. So let's call that about 90,000, I think, somewhere around there. We'll approximate that. Ish. The energy, finally, the final energy then is going to be equal to what? The original energy also increased by the size of the dielectric constant. So this was going to be equal to our 3.4 times the 150 microjoules. So this guy is going to be equal to something like 440. An extra 0 microjoules. So 4,400 microjoules. Oh, too many zeros. There we go. What's up?
Can you go back to the problem?
Sure.
Okay, the battery is this.
Batteries gets, yeah, that's, yeah, everything would be different in the batteries. Okay,
It's
so
just gonna be the opposite, right?
yeah, it would just be the opposite. So now that would decrease instead of increase. So finally, the last part then says, what was the work done to remove the dielectric? Who did the work? So let's talk about that. So in this case, so finally, what we know is, so our work then is going to be equal to our change of potential energy. So our change of potential energy then in this case is going to be equal to the final potential energy minus then the initial potential energy. So in this case, this is then going to be a positive number because it went up. So this works out to be about 110 microjoules. Now in this case, it's asking who did the work. Now notice what I'm writing here is the work is equal to the change of potential energy, not negative the change of potential energy, which means I'm looking at this from the viewpoint of an external agent. Remember, if I look at it with a negative change of potential energy, that means I'm looking at with the electric field. The fact that this thing is positive means that the external agent actually did the work. So in this case, this is an external agent. This goes back to what we were talking to Tim about, right? So again, if we're inserting the dielectric, the electric field itself pulls it in because it wants it to be there, which means if I pull it out, means the electric field doesn't want it to be out, it wants it to be inside, so something else has to grab it, pull it out, to move it outside of the place to make sure that it gets outside, which means that this makes sense that it had to be an external agent. Okay, what's up?
So on the instructions of the problem, did it say the battery is disconnected just to remove the?
Correct, yes. So we go back to here, so it says first we charged it with the battery, then we disconnected it from the battery, and then we did everything. Correct. So it's opposite of what we talked about. What's up, Omar?
Wait for the change in work.
Yep.
The change. Which numbers are you subtracting?
Oh, so in this case, I'm looking at, so if I go back, I'm looking at this number here and this number here. So I'm subtracting those two. Assuming I know how to subtract, which I don't know. Looks like it's actually more. But that's fine. It's just. I'll check those numbers later. So good. So that's it. So it's the end of this chapter. So the last thing is bring up quickly. We got about 5 minutes to work on it, but it's a start. So, group assignments. So here I actually have 2 for you. So I have these 2 beautiful things. The first one has to do with this wonderful monstrosity. So this says we have the circuit, the capacitors below. So each one of these capacitors has exactly the same amount of capacitance, which is simply equal to 7 microfarads. We have our battery here, which is our EMF, which is supplying a 15 volts EMF to this guy. And from here, we just want to know a whole bunch of different things. So what is the equivalent capacitance of the circuit? So by adding these 4 guys together, what's the equivalent capacitor? What is the charge on the equivalent capacitor? And then what is the, finally, potential across each one of these 4 capacitors? And what is the charge stored on each one of these 4 capacitors? So this is what we were doing last week. So not too bad. Again, here, first thing you have to do is identify what's in parallel and what's in series. First, collapse things that are in parallel in this case, and then collapse everything in series. Find your equivalent capacitor, find the charge. Since this is connected in series with this guy, connected in series with these guys combined together, they all then have to have the same exact charge on them. And then from there, you can find all the potentials and everything. The second one has to do with what we're doing today. So we have a parallel plate capacitor, which has a plate area of 8.5 centimeters square and is air filled, which means the dielectric constant in this case is simply equal to 1. And they're separated by a distance of 3 millimeters and charged by a battery which has 6 volts worth of potential. So that's my EMF. Then says we're disconnected from the battery, and then we're going to pull apart the plates of the parallel plate capacitor to increase them from an initial separation of 3 millimeters to a new separation of 8 millimeters. From here, what I want you to do then is find a whole bunch of stuff. So again, first, what is the potential difference between the plates initially? The initial energy which is stored, the final energy that is stored, and then finally, what was the work done to separate these 2 plates and who did it? Was it the electric field or was it some sort of external agent? Okay, so we kind of draw what this one is talking about, so we know this is the second one. So initially, here are my plates. This has cross-sectional area A. It's called that the initial distance of D, 0. These guys initially are attached to the battery, and then this thing is going to accumulate some charge Q and negative Q. Then I'm going to pull this thing out from the battery. So this thing's going to be sitting simply here. So again, cross-sectional area, separation distance D, initial charge Q and negative Q. Then from here, I'm going to take this thing and pull it apart so that my top plate's going to be here, my bottom plate's going to be here. So this is at a new distance of D prime, same cross-sectional area. So what are all these different things? So what now is, so what's the potential here? Call that the initial potential. What's the final potential here? And what's the energy stored here? You call that U initial. What is the energy stored here? Let's call that simply U. And then finally, what is the work done to separate these two plates? And then finally, who did that? And just to make sure that we know who actually did the work, if I have a positive plate and a negative plate, what do they want to do to each other? They're attracted to each other. They want to be as close to each other as possible. Which means if it starts out here and then I move into here, did the electric field do that? Absolutely not. So who actually did it? External agent. So me. Okay? So just make sure that when you calculate your numbers, you know which one, what your correct answer should be when you get to this part. So if you look at this as the work done by the electric field, which again is negative to change potential energy, this thing better be negative, or you know you got the wrong answer. So something was wrong someplace else. It was okay? We have 2 minutes to discuss with each other. Or you call it.
What chapter was this starting with?
I'm sorry?
What chapter number was it?
Oh, so this is the end of 26. So tomorrow we're gonna start 27.
Was the that one we were interval we did at 25 or 26?
I don't remember. It's technically part of 25 because we actually did part of 26. But I think 26 had to do with the gradients. So the relationship between the electrical potential based off of current. So that, even though we did that earlier, I think that was the beginning part. But the other part, no, the interval versions, continuous objects, that was all part of that. All part we did there.
So I should be able.
You can do everything through 26 now. Yeah. Yep. And then tomorrow we'll start 27. So 27 we'll start talking about resistors, currents, and all that kind of good stuff. Current densities, drift velocities, all these things we kind of talk about.
I went to. Find out if you were, see your point.
Yeah.